Uh, Let me introduce myself first. I'm Tan Zhao. I'm from NVIDIA, and I will co-organize this industrial web series today. Today, our speaker, Dr. Dong Wei, is a senior researcher at the Tencent Jarvis Lab. Dr. Dong Wei received the PhD degree in computer engineering from the University of Singapore in 2013. From 2015 to 2018, he was a postdoc researcher at the Computational Biomarker Imaging Group Center for the Biomedical Image Computing and Analytics, University of Pennsylvania. Since 2018, he has been a senior researcher at the Tencent Jarvis Lab, Shenzhen, China. He is the author of more than 30 journal and conference papers and more than 10 inventions, and the main algorithm developer of the Tencent MICCAI CT image-assisted pneumonia triage and assessment software. His research interests include the broad area of computer-aided medical image analysis, with the current focus on data and annotation-efficient approaches. Dr. Wei is a member of MICCAI Society and received the MICCAI Student Travel Award in 2011. Today, his topic will be data and annotation-efficient deep learning for medical image analysis. Dr. Wei.
Thank you for the introduction. So I presume you can hear me. And let me share my screen. Start the. So can you see the slide?
Yes, I can. Yeah.
Okay. So thank you very much for the introduction. So it's my pleasure to give this talk. Today I'm going to present some of our attempts at data and annotation-efficient deep learning for medical image analysis. So as you can see, it's a big topic actually. So yeah, maybe some attempts. And so before that, allow me to introduce my affiliation a little bit, because we are a relatively new lab here. So Tencent Jarvis Lab is established in 2018 in Shenzhen, China, and it's a laboratory dedicated to medical AI. Here we are committed to building a real-time knowledge and decision-making platform for Tencent healthcare through machine learning and big data analysis. And we also aim at providing safe and reliable AI products and accelerating the marketization in the medical field. And by the way, we actually have been a platinum sponsor of the MICCAI conferences since 2019. And as we can see, Tencent Jarvis Labs comprises 3 groups specialized in medical imaging, natural language understanding, and medical big data, respectively. Here we are proactively exploring cutting-edge AI technologies. So since its establishment, we have published more than 90 top-tier conference and journal papers, invented more than 400 medical AI product patents, and won more than 10 international medical AI-related competitions. So now let's jump to the topic of today's talk. And I think the big question is, why do we need this data and annotation-efficient deep learning for medical images? I guess the motivation actually for the audience today is pretty clear. On the left-hand side, I show the natural images, and the famous ImageNet actually drives the evolution of the modern neural networks. These networks are deep and wide, and they can automatically learn representations. And the bad thing is when your paradigm actually hungers for annotated data. And fortunately for natural images, these data are easy to collect and annotate. So they have usually low-cost generators like handheld cameras or camera phones. And they can use a web crawler to collect and use crowdsourcing to annotate. On the other hand, medical images now also enters the era of modern neural networks. However, they are more difficult to collect and annotate. They often require professional, often expensive equipment to generate, and the existing data are actually often housed by healthcare institutions that cannot be shared easily due to various concerns. And To annotate them also requires expertise, and lastly, actually for some rare diseases, the data itself is very limited. So today I'm going to talk about 3 of our research works along this direction. The first one is based on anatomic consistency, the second one based on metric learning, and the third one is based on unsupervised representation learning and self-distillation. So the first one is few-shot segmentation driven by anatomic consistency. Unlike natural images, medical images of human bodies actually display highly consistent anatomy among individuals. Therefore, as shown here, if we are given an atlas and a label of the atlas, then we can actually register this atlas to the target image to segment. Then we can also transfer this label using the same correspondence to obtain the segmentation. Actually, there are many classic methods for registration. However, they are not computationally efficient. Recently, the deep learning-based registration is also developed, and they are usually unsupervised, and the inference can be fast once trained. Here, I show the inspiring work of Waxmoff. So if we are going to use this framework for one-shot segmentation, we can actually abstract it like this. So given the atlas and the segmentation, we can input the atlas and the unlabeled image to generate the deformation field. Then walk this atlas towards this unlabeled image. At the same time, we could also use this deformation field to warp the segmentation of the atlas to get the segmentation of the unlabeled image. And in this framework, actually, the supervision signal are twofold. The first one, the image similarity between the warped atlas and the unlabeled image. The other thing is the transformation smoothness on the deformation field. This is actually a regularization term to avoid unrealistic deformations. So it is usually the spatial gradient. This is a very inspiring work. However, we think this framework is not fully utilizing the supervision transformation information provided by the atlas for, especially for one-shot segmentation. Therefore, based on deep learning registration, we propose the label transfer network, or LTNet for short, for one-shot medical image segmentation. So here we innovatively incorporate cycle consistency and enable multiple extra supervision signals in the image space, transformation space, and the label space. So let's go through them one by one. The first is in the image space. So we can actually add another transformation to transfer or to deform the warped atlas back to its original form. In this way, we can actually use the image consistency between this original atlas and the reconstructed atlas. Here we use L1 loss. So this cycle consistency is actually quite classic right now. Then in the transformation space, in terms of forward and backward consistency, the same is the correspondence should be reversible, meaning that a voxel warped from one position to another in the forward path should be warped back to its original position in the backward path. So we have this loss here. So a point is warped, the displacement of point in the forward path, and this is displacement in the backward path, and their summation should be 0. If it is not 0, we impose a punishment. Then in the label space, we have 2 losses. The first one is the same as in the image space. So we actually have the segmentation of the original atlas. Then we warped it for the unlabeled image. We warp it back in the backward path to reconstruct the original segmentation. And this should be the same. Therefore, we impose a dice coefficient loss here. Then secondly, the difference between the structure of the atlas and the unlabeled images should be consistent in the forward path and in the backward path. So here we actually impose another loss. And finally, adversary training is an effective strategy commonly used in GAN. So we also incorporate it. Here, however, we cannot judge whether a deformation field is true or false. Therefore, we employ a delegation strategy to differentiate the real unlabeled image and the one warped from the atlas. In this way, we just get rid of the problem of about the reality of the deformation field. And then the total loss actually is weighted summation of all the losses mentioned above. For experiments, we collect 103 MRI volumes from the candidate set, and we divide them into 83 and 20 for train and test. And for the atlas, we actually choose the one that is closest to the anatomic average in the training set. Here, first are some visualizations. In the bottom row on the left, we can see that this is actually the warped atlas, and they are very close to the unlabeled image. And on the right-hand side, we actually show the one-shot segmentation of Voxmorph data.org and our proposed method. And the unit here is the upper bound trained with all the fully supervised volumes. As we can see, for the parts pointed by these red arrows, our method actually are better. Then we conduct ablation studies to validate the efficiency of the proposed losses. First, based on the Voxmorph, we add the gun loss and the cycle gun loss. As we can see, they are effective to boost 3 points. Then on top of that, we add in the losses in the transformation space as well as in the label space. As we can see, individually they play they play some effect, and jointly they reach the highest value of 82.3 dice coefficient. Then we compare to different methods, and on the left-hand side, we actually compare to a multi-atlas methods, MapMIS, which is a classical registration method. As we can see, our LTNet using only one atlas actually outperform MapMIS using 5 atlases slightly. On the right-hand side, we compare our LTNet with Voxmorph and data.org, both of which are the deployed methods. As we can see, again, our LTNet are the highest in min dice, minimum dice, and maximum dice. However, we do notice a gap here compared to the UNet trained with all the available volumes. So that's pretty much the first thing. And actually, RTNet is based on the assumption that the anatomies are the same across patients. So what if the anatomies are actually different? For example, their lesions. To take them into account, we developed the IDA net to actually, the key here is that we identify the individual difference by a forward and backward consistent check. That is, a voxel is considered as belonging to a single individual when the displacement between the forward correspondence and the backward correspondence is too large. So here, if we look at here, we actually still have backward and forward, and we do a consistent check. The thing is, if we remember this term, they should be summed to 0. Otherwise, we impose a loss here. However, if this term is too big, it will not be smaller than the right-hand side. In this way, we consider it to be individually different pixel. So given this criteria, we can actually get the forward and backward difference maps as shown here. So they are binary maps. The white pixels indicate some places that are individually different, and black parts are shared across across the patients. Then when we calculate the similarity loss between the two images, we actually exclude those individually different regions by this term. Noting that we have a regularization term here, which basically says the network cannot put mark or all the pixels to be individually different. In that case, the null solution should be that all the pixels are marked with individual different, then in that case, there will be no loss at all. So we have this regularization term. So for experiments, we do the abdominal multi-organ segmentation comprising 90 CT volumes, and there are 7 organs for segmentation. We randomly select 20 for test and use the others for training. And it is worth mentioning that the abdominal organs can present larger deformations than the region. Thus, the task is more challenging. So as we can see here, our IDA baseline actually is closest to the upper bound of UNet and the ground truth. Here we compare to this one, which is classic registration data.org, and our approach is at TNet. Quantitatively, IDA.net is better than the data.org, as well as our previous work here. So as we can see, we reached 61% dice coefficient in one shot. Then we extend IDA.net for future segmentation with 2 to 5 atlases. As we can see, the results actually gets better with more atlases as expected. In addition, we conduct ablation experiments to validate the efficacy of the proposed awareness of individual difference in the five-shot setting. As we can see, the results show that the individual modeling actually brings a 3-point improvement on top of the cycle consistency. We also compared to sorter methods in the 5-shot setting. As we can see, here is the classic registration methods and data.org, and our approval is at TNet. So our IDA baseline actually achieved 68%, which is a much higher, substantially higher than the other methods. Note that the future performance is again obviously inferior to the upper bound. So actually, it is more obviously than for brain tissue segmentation. I guess it's pretty much for the first part. Then the second one is future segmentation based on deep metric learning. So in the registration-based methods, actually they can deal with limited annotations. However, they require unlabeled data, abundant unlabeled data to train the registration. However, in some cases, like for rare diseases or new diseases, there can be limited data as well. Therefore, we propose this MRE-net to effectively utilize inter-subject similarities and the inter-class variations. And it is metric learning, so it is based on distance. It is non-parametric, thus robust against overfitting. And compared to atlas-based methods, it is more robust with respect to large inter-subject variations. So here, we use the MRI brain tissue segmentation, for example, to explain the 3 elements of our metric learning. So the first thing is it is distance-based. And the second thing is there should be a learnable projection function to project the input to an embedding space where the prototypes of various classes exist. So in this part, then our learning target is that samples of the same classes are close to each other, whereas those different are far away. Therefore, after the training is completed, we project the test samples into this embedding space and classify them according to the distances. For example, this E1 should be classified as the same class as C2, basically nearest neighbor. In practice, however, we used more complicated methods than nearest neighbor, which is explained next. So here is the complete framework of the proposed MRE-net. Part A is a simplified 3D UNet backbone for future learning. Then in part B, we propose to extract more information from the backbone. Concretely, we concave the feature maps on the right-hand side of the UNet to collect features at all levels. Then we concatenate Cartesian coordinates as additional information, as many tissue and organs are location-specific. Further, to make it robust against the diversity of the segmentation target, we fit the feature maps through a squeeze and excitation attention block and ASPP module for obtaining channel selective multi-scale features. Then finally, we reach the part C, which is a multimodal representation learning via the cosine normalization technique. And next, we will describe it in details. So as I mentioned, the first element is the distance function. So here, denoting the distance between an embedding vector and a category prototype by this d. Then the probability of x belonging to the case category is actually proportional to the negative distance, to the exponential of the negative distance. Then we can compute the class posterior with a softmax operation over all the candidate categories. This is pretty straightforward. Then let's consider the cosine distance, which actually is 1 minus the dot product of this normalized feature vectors and the class prototypes. Then it can be easily derived that this posterior is a softmax over the dot products. And then the dot product can be actually implemented using an FC layer with our biases set to 0, and CK is a weight vector connected to the case output node, and each node represents a category. In this way, the cosine distance can be actually implemented with a commonly used FC layer, and the category prototypes are embedded as the weights of the FC layer, basically here. Now let's extend it for multimodal learning, where category is represented by a set of prototypes instead of a single one. And then as shown here, so a category actually is a set of a set of prototypes, and CKJ is the center of the JS mode, and M is the number of total modes. And then each prototype gives an individual probability, and the multimodal mixed distribution is defined as a weighted summation of all these probabilities. And here alpha is a mixing coefficient, and for a specific category, they sum to 1. Then the posterior is still a softmax operation over all the classes. The only difference is that every class is now represented by a set of individual probabilities. Conveniently, this multimodal distribution can still be implemented using an FC layer. Again, the biases are set to 0, and here the weight matrix of the FC layer actually is a collection of all the multimodal prototypes. So as we can see here, we show this multimodal representation actually is a big matrix, and the matrix comprises all these multimodal categories. Then, okay, now the question is how to set up the mixing coefficients. An intuitive way is to simply average all the different individual probabilities. However, in this work, we propose a self-adaptable mixing coefficients for each category's multimodal distribution. Here, I do not jump into the details, but the thing is, we use a modified squeeze and excitation module to output the class-specific and class-specific mixing coefficients for each model of each class. Here, then we put it all together. When a pixel needs to be classified, we put it through the multimodal representation using the cosine similarity to obtain the multimodal probabilities. On the other side, we use this input embedding to get the adaptive mixing coefficients. Then we put them together to get the posterior. As segmentation is actually dense classification, the each voxel is simply predicted as the class of the largest posterior. And for training, we actually use a simple cross-entropy loss for training. And the three parts, A, B, C, are trained end-to-end together, including these multimodal representations. For experiments, we actually do the brain tissue segmentation in MRI and abdominal multi-organ segmentation in CT images. So here we compare the ends, which is classical registration methods. We also compare to UNet in one shot, our methods in one shot, our methods in 3 shot, and our methods UNet in 6 shot. For abdominal multi-organ segmentation, our method is done in 1 shot compared to UNet in 6 shot and UNet in 20 shots. It might be a little bit difficult to see here, but our methods actually produce better segmentations than UNet, as well as ends. We conduct experiments on the brain MRI dataset to determine 3 important design options. For the mixing coefficient, we compare to 1 hot and average. As we can see, the proposed adaptive approach achieves the best performance in terms of both the dice and the HD matrix. Then we vary the number of modes from 1 to 5. And in both 1 and 3 shot settings, the performance first increased and then fluctuated as M increased. So for a comprehensive consideration, we select 3 modes for following experiments. Then we validate the choice of the metric. On one hand, the performance of Euclidean distance is slightly lower than that of the cosine, but not that much. For example, the dice on the MR brains is 77 against 78. However, Euclidean distance consumes substantially more resources. As we can see here, it consumes more than 2 times of GPU memory and about 1.7 times time duration for training. Therefore, it is apparent that our choice of the cosine distance is beneficial. Then for quantitative evaluation, let's maybe directly look at the mean values in the last column. As we can see, in 1 shot setting, actually, the ends is pretty good. It achieves 71% dice. However, for UNet without augmentation, it's pretty bad, only 17. After adding the augmentation, it jumps to 52, but still not satisfactory. On the other hand, our method actually achieves 81 with only 1 training sample. Then we increase the number of training sample from 2 to 3. As we can see, the performance gradually and steadily improves. And it is worth mentioning that our 3-shot performance actually is better than the 6-shot performance of UNet. Then for the low-shot multi-organ segmentation, actually is more challenging, mainly for 2 reasons. First is the contrast of soft tissues in CT is not as good as that in MRI. And secondly, the intersubject variations in both appearance and structure can be much larger. In this case, as we can see, neither ends nor the UNet managed to produce reasonable results for this challenging task. On the contrary, our framework achieved 69 dice with only 1 training sample. It is actually even better than UNet with 6 samples or with 20 samples. Lastly, as we compare to the non-low shot performance reported in 2 SOTA-related works, apparent gaps were observed between this dense VNet. For example, for this one, ours are 52 and here is 73, and for this one, ours is 56 and this one is 71. On one hand, if access to many fully annotated data is provided, maybe it is always better to design more powerful models of larger capacity to make full use of the data and annotations. On the other hand, our work was focused on the data scarcity problem. So instead of trying to build non-load short methods training with abundant data and annotations, and here our experiments actually shows the effectiveness of our proposed method in producing reasonable segmentation in the target scenario. That is to say, we should look at this thing from different perspectives. So for ablations, we conduct experiments to find out the contributions of individual components. The incremental experiments from row A to row E actually shows that the distance metric learning is the most crucial thing. For example, on the brain segmentation, without distance metric learning is about 15% for dice. Then with this distance metric learning jumps to 65. To further validate that, we also try to remove the distance metric learning from the complete model. So if we look at the row F, we can see the performance actually drops by more than 50% from the complete model in row E. At the same time, actually, other components are useful too here in gradually improving the performance, but not as important. So here, a little bit discussion on why our MRE-net works. I think the first thing is metric learning, which fully utilizes the inter-subject similarity, and its non-parametric form is robust against overfitting. Then secondly is the multimodal learning to effectively exploit intra-class variations. That is to say, even for the same organ of different patients, they can appear differently in different images. And in the extreme case, is even for the same organ of the same patient, it might just display natural clusters of appearance. Therefore, our multimodal learning actually is able to capture this intra-class variation. And lastly is a self-adaptive mixing coefficients to allow voxel level adaptation of the mixing coefficient. So more intuitively, we visualize the feature spaces learned by our proposed MRE-net and the 3D-UNet. As we can see, the clusters by our method is more separable and more compact. Actually, they are more separable actually means that different classes are farther away and they are more compact actually means that the same class are close. This actually well aligns with the goal of metric learning. Okay, the third case is about unsupervised representation learning and self-distillation. So this one is mainly for rare diseases, which is a significant public health issue and challenging to healthcare globally. And the challenges include delayed diagnosis, misdiagnosis, and lack of sufficient data. Not to say to train the deep networks, the data is not sufficient to train maybe the doctors as well. So there are some existing works on rare disease classification. However, they all relied on heavy labeling of the base data sets, and the meta-learning process and the target task are often isolated. Therefore, we propose to explore future medical image set classification using our unsupervised base data set. At the same time, we propose to inject knowledge about the rare diseases into representation learning. So this here, this is the framework of our proposed method. We look into each step one by one. The first step is unsupervised representation learning on common diseases, normal controls. So noting that this database actually is a collection of common diseases and normal controls, which is big. Here we use the MOCO V1 for the contrastive learning for unsupervised representation learning. After that, we freeze the feature extractor here. Then we append a simple classifier as a baseline model. And this baseline model is trained on the small data set of the rare diseases using probably whatever suitable classification loss. Then in the third step, we freeze the baseline model entirely. Then we generate pseudo-labels for the base data set. So here, note that we are actually generating labels of rare disease for the normal disease samples. Then in the last step, we conduct the self-distillation where hybrid unsupervised and pseudo-label supervised representation learning. So if we look at here, actually it has two parallel processing lines. In the first one is normal classification line, where we try to classify the base data set into the pseudo labels with a classification loss. Noting that here both feature extractors and the classifier are reinitialized. At the same time, in the bottom processing line actually is still the contrastive learning process. Therefore, our distillation loss actually comprises two parts, one for the pseudo-label classification, the other for contrastive learning. So we call it a hybrid representation learning. Here is actually a notion of learning rare classes from common classes. Given an example, this is a symbol of Singapore, which is a place of this year's MICCAI. So actually we can learn it by learning the line and the fishes. That's learning rare classes from common classes. Then for experiments, we use the ISIC 2018 skin lesion classification datasets. We treat the 4 classes with most cases as base class. Then we treat the other 3 classes as rare diseases. Therefore, our tasks are 3-way and K-short. Then we here compare to many different sorts of feature learning methods. Here, the training from scratch is used as a baseline. Of course, it works. Then we compare to the group of supervised meta-learning, unsupervised meta-learning, supervised representation learning, and unsupervised representation learning. Our major findings are as follows. So first, the representation learning-based methods actually are generally better than those meta-learning based methods. And secondly, it is a bit surprised that the unsupervised representation learning actually are generally better than supervised representation learning for this task. Then lastly, our proposed hybrid approach actually achieves the best performance in the group of unsupervised representation learning, also the sort on this task. To validate the efficacy of the proposed hybrid distillation, we conduct population experiments. So here, the first row is the baseline model. Then we distill with the classification loss alone. Then we add the contrastive loss. So the results show that distilling with the classification alone actually also brings moderate improvements upon the baseline model, suggesting the efficacy of injecting rare disease knowledge into representation learning. So basically, it validates the effects of learning rare diseases from common diseases. Then when distilling with the proposed hybrid loss, we achieved further appreciable improvements. And actually, this is the best performance in this work. And we conjecture that this is because the contrastive loss actually helps avoid overfitting to the support set of the rare diseases, which may be affected by noise and bias due to small size. So this hybrid setting is actually efficient. Now I think it's time to conclude this talk. And so a little bit review of what we have talked about. First, our works on few-shot medical image segmentation. On the left-hand side are the works in CVPR and triple AI. So it is suitable for limited annotations, but with much data to train. And they are based on registration and cycle consistency. So they can handle modest inter-subject deformations, such as brain registration. On the right-hand side is the TMI 2020 work, and it can deal with scarce annotations and scarce data. And it is based on multimodal representation learning and metric learning. And due to its formation, it can better handle large inter-subject deformations, such as abdominal organ segmentation. Then the third work is few-shot medical image classification. So the key idea here is to learn rare diseases from base classes. And it is based on unsupervised representation to learn the baseline model. And then in the last step, we use a hybrid distillation, integrating the pseudo-label supervision as well as a contrastive learning for a effective classification model. So conclusion here is that deep learning has great potential, yet with great challenges for practical application. In this work, we look at the problem of scarcity of annotations and data for medical image segmentation and classification. So we have made some small steps here, presenting some works. And however, I do believe there is a long way to go. As I kept saying in this talk, the gaps. Actually, I kept mentioning that the gaps between the few-shot learning methods and the fully supervised methods. However, I do believe if used properly, this few-shot learning method should play some roles in the clinic settings and research. So here, this is a list of the works I talked about today, and thanks for your attention. Questions are welcome, and if you would like to, you can also email me for questions.
Thank you, Dr. Wei.
Yeah, that's all.
So it's time for questions. You can raise your hand or type your question in the chat box. So I have one question. You described two few-shot methods, case 1 and case 2. So if you compare these two methods, which one works better?
That's a very interesting question. So I think first of all, they are suitable for different scenarios, as I mentioned here. So maybe for brain segmentation, they are roughly the same. And however, for the abdominal multi-organ segmentation, the TMI work, the metric learning-based work might be better. On the other hand, in the registration-based method, we actually, the extension looks into the problem of individual difference. So if there is individual difference, then the registration-based method might win again. So actually, it's really depend on the scenario of usage.
So what's the most important reason? I mean,
so I think the most important reason is that in registration-based methods, no matter classical or like deep learning-based, they still cannot perform very well on large deformations such as abdominal organs. So I think that's a key difference between their performance difference on abdominal organs. on the right-hand side, these metric learning-based methods, it's not registration-based, so it is more robust on abdominal organs.
I see. Thank you.
Mm-hmm.
There's a question. Are there any ideas or future scope to integrate federated learning approach to your proposed models?
Thank you for the question. So, in fact, I haven't been considering that, but I think that's a pretty nice direction. The thing is, we are trying to deal with shortage of data here. In federated learning, actually, I think there might be a lot of data, but they are at different places, and we just cannot put them together. So I think there might be some nice integration of the two. However, really, we haven't done that yet, or haven't considered that scenario. Yeah.
Yeah, thank you. There's a question from Tim. Thank you for the talk. If the scarcity of the annotations is a major pain point that is mentioned during most of the talks in the recent past, would it not make sense to invest more time and monetary resources into data labeling? To me, it seems that 95% of the researchers work on architecture topics, while at the same time, everyone points out that data is a huge issue. That seems rather contradictory.
Yeah, I mean, maybe that's not problem of the methodology. So just now, the previous question is about federated learning. So here we actually, in the first place, we consider that we have limited annotations, but we have much data. Then on the right-hand side, we say the data is limited as well. So maybe in practice, especially in industry, to develop a really like a deployable model, the best way or the more robust way is to simply collect more data and annotate them. However, in that point, to that end, I actually agree with the comment that maybe labeling more data, labeling more data is a better way. However, I think the research here still makes sense. For example, in the development of a new imaging modality in the early time, maybe the clinicians just want to collect a small set of data, and they want to like see whether their assumptions are valid or not. So the data is really limited. Then another example might be that there are new diseases such as COVID-19 we had since 2020. And then in that case, in the early outbreak of the disease, the data are limited, really limited. So as I mentioned in this talk, kept mentioning actually, if we have access to a lot of data and annotation, maybe it's still better to do the fully supervised methods. However, in some restricted scenarios, we might still consider the future learning. And in the future, it's hard to say whether this future learning can ever match fully supervised models. I cannot say that, but in some restricted scenarios, they might play some roles, I guess.
Thank you.
I hope that answers the question.
Thank you. The following up question from Yashasvini. Appreciate your answer on FL. What does the future model address domain shifts in terms of hospital protocols, disease, severity, etc.?
Yeah, that's a very good question. So in these three works, we haven't dealt with that problem. However, that's a legitimate problem. And actually, I have seen some works in natural image domain, actually in general computer vision. They are setting some scenarios that in the future learning problem, there is also domain shift. And I think that's a good step. But honestly, we haven't been doing that in these 3 works.
Thank you. Do we have more questions? So if we do not have more questions, I think our talk can, we can close this talk. And thank you so much, Dr. Wei, for your talk. And yeah, this is Dr. Wei's email address. And if you have any further questions, you could email him. And I recorded the video. I will send the video to you, Dr. Wei. So if you would like, you could upload the video by yourself.
Thank you, Matt.
Thank you. Bye.
Bye.